electrical energy distribution and consumption. So I will ask each one of us to be ready for it. And since we have started late, if we delay, please have to bear with us. So hope all of us can be able to see the screen. Please, if you don't hear me well, you let me know such that we can communicate to each other well. Today we are looking at electrical energy consumption and distribution, which is a sub theme, or it's a topic that we talk about when we are looking at electricity. So I'm sure by this time, each one of us knows that electricity is a form of energy. So if I talk about electrical energy, each of us will know that electrical energy is a form of energy. So in this lesson, we are going to be talking about how electrical energy is distributed. But before distribution, we have to talk about how briefly, how do we generate it? Then if we know how it's generated, then we will know how it is moved from one place to another, which is the distribution. And then after distribution, that is when we will talk about how it is consumed, or how the consumption takes place. So this is asking ourselves, how is electricity generated? So I want to hear from you people. How do you think electricity is generated? Someone to share with us. How do you think electricity is generated? Let me have hands. And yes, you can talk to us, please. Treasure?
Yes. I think
Yes.
it's through turning, like when our current flows through a circuit, the electricity is generated. But in terms of distribution, I think it's got through turning of turbines.
Okay. You've said when something about a circuit. I didn't get well. Andrew?
Okay.
Yes.
Electricity, thermal power plants, burning fossil fuels. There is coal, natural gas, or oil to produce steam, which drives a turbine connected to a generator. And there is also the nuclear power plants. They use the nuclear reactions to heat water and produce steam, which drives a turbine and a generator. That's what I know.
Okay, thank you, Andrew. There is this one here, though he's using the phone name. Zomi, your name, but you have to rename it. So your hand is up, so you give me the answer which you have. I think it's not with us. Linda?
I think it's generated from a turbine, and a turbine converts mechanical energy to electrical energy. That's all I know.
Okay, so the turbine does change electrical energy to mechanical energy, sorry, to electrical. Yes, Big Daddy. That is how you call yourself. How is energy?
No, that was my answer. That was my answer.
Okay. Riley, I think Riley will be the last person on this. Yes, Riley. Riley's hand has gone. There is someone using ITEL. You can unmute and give us your answer. Okay, if we don't have more answers, then let's continue and see how electricity is generated. So in this, they're telling us that electricity is generated from, like Andrew, I think it was Andrew who told us that electricity is generated from a lot of things, but these things that we have coal, we have nuclear reactions, we have falling water, but all these things, what they do is that they produce energy, which energy is used to run turbines. Turbines are like, if in simple terms, they are like fins that when they turn around, they generate what we call mechanical energy because they are moving at a very high speed. So when that mechanical energy, it is that mechanical energy which is then converted to electrical energy through a generator, which these turbines are running, and then we get out the electrical energy that is then transmitted and used in our homes. So electricity is generated at power stations by using any of those things. We can have nuclear power plants where nuclear reactions are the sources of the generated power or energy. There is where they use coal or oil, and these ones are used to generate heat. That heat is the one that that helps in running the generators that thereafter generate the electricity that we use. Then we all know the hydroelectricity power, how it comes about. It's that they put turbines at the point where we have waterfalls, so that the energy that the potential energy that the water falls with to the ground is that energy that is used to run the turbines, and those turbines then are used to run a generator which will generate the hydroelectricity power, which is then transmitted to different parts of the country for usage. So briefly, that is how electricity is generated. In the chat, we have someone saying fast flowing water or turning of turbines by water as sources, and those are really correct. So after this water has been generated, then the next thing after generation is transmission. So how is electricity transmitted? Any person to tell me now? If we have generated it, let us say we have generated it at a power station. We are talking about like here, any power stations that we know around the country that we can use as an example. Anyone who knows any power station around the country that we can use as an example? Yes. Yes, Linda?
Bujagali Power Station.
So if we have that one, if we have Bujagali Power Station, and the water from the Bujagali Falls has turned the turbines that they put there, and now it has made the generator to run, and the generator has now produced the electricity energy. How is that electrical energy distributed? That is our question now. How do you think this electrical energy is distributed? Someone who can share with us. How do you think this electrical energy is generated? Hands up. Ficats, your hand is up. You unmute and tell us what you think.
Okay.
Yes.
Electricity is like after electricity is generated, yeah?
Yes.
At the power plant, it goes through a step-up transformer. These transformers increase the voltage of the electricity to a high level, typically in the range of thousands of volts. So, high voltage, yeah, is used for long distance transmission because it reduces energy losses during transportation of electricity. So, I think electricity is transmitted by the use of transformers.
Okay. We have by the use of transformers. Yes, Tendo. You also give us your answer.
Teacher, I think electricity is transmitted using electric wires and electric poles.
So there is one who is told us generators. The Nintendo is telling us electric wires and electric poles. Yes, this person with ITEL, please rename yourself so that I can call you your name. But your hand is up, you can give us your answer. I think his hand is not speaking, so we will go to someone else.
I think it is stepped up to high voltages before transmission using step-up transformers.
Please mute your microphones after you have given us your replies. Okay. We have talked about poles, we have talked about wires, cables, we have talked about transformers. So we have something here. We are talking about transmission of electricity, and they have told us that first of all, the electricity is generated at the power station. We have seen how it's generated, and it is stepped up. It is stepped up. So stepping up, why? It means that first of all, as we are generating it to a certain value of voltage, which is not enough for us to transmit. So the reason why they came up with a step-up transformer, like our friends have said, is such that the small voltage that we get, or that small value of voltage that we get, can be made higher using a transformer. So what the step-up transformer does is to transform a small voltage to a high voltage so that it can be transmitted. So the reason why a step-up transformer is important, it's because it steps up a small voltage to a high voltage for transmission. That is what we should note first. Then we have, sorry. Then we have, they have continued to tell us that the electricity that is transmitted, it is here, the electricity is transmitted at high voltages to reduce power loss through heating process in the transmission, and they're telling us that the transmission cables are thick. They are thick transmission cables. So we are going to pause and ask ourselves what causes the power losses, and then why do we think that these cables for transmission are made thick? So we are going to ask ourselves two questions. One, let me put it somewhere here. So one question that we are going to ask ourselves is, why there are power losses. That is one. Then the other one, why are there power losses, is the first question. Then the second question is going to be, why are transmission cables made thick? So any of us who has answers to these questions? Why are there power losses? Someone to share with us. Why do we have power losses? Yes, Junior?
Due to resistance.
Due to resistance in the wires, right?
Yes.
Okay, thank you, Junior. Yes, Blaze, your hand was up, but I think you left. Yes, Big Daddy, you give us your answer, and then Stephanie will also give us his answer.
The cables are thick because they have a lower resistance, which allows electricity to flow through them without loss of energy, of heat energy.
Okay, thank you. Stefan, your hand is up.
I think it's due to the heating effect in the transmission cables.
What heating effects in the transmission cables? That is why we have power
That's
loss.
all.
Okay. Yes, Braze.
I think the reason why there are power losses because of power surges and short circuits at the where they produce from electricity.
Okay, thank you. Riley, your hand is up. I think Riley is not with us. Cantono, sorry. You unmute and give us your reply.
Sir,
Hmm?
I'm just trying.
It's okay.
For me, I think there is power loss because some power is lost into heat energy during the transmission of electricity. That's all.
Okay, some power is lost as heat energy. Yes, there is heat energy that that causes the power loss, and that power is So I was saying that the reason why we have power losses due to heating effect is because inside those wires, those wires have resistance. So the power due to resistance, there is power that is lost, and that power is lost has heat energy. Electrical power, we will learn, if you have not yet learned, we will learn that electrical power is got from I squared times R. No, squared R, I think it's IR. Where is my wrap bound? So we have our electrical power lost due to resistance. So the reason why we even have thick electric cables is because that those electric cables will help us to reduce the resistance, because resistance and area of cross-section are inversely proportional. That when we have a big area, then we have a small resistance. When we have a small area, then we have a big resistance. So because the reason why they are made thick is to reduce their resistance such that they reduce the power losses as power is transmitted from where it's where it is produced from to where it's being consumed from. So those are the reasons why in our document here that we are following, they are telling us that the high voltages are transmitted. The reason why we have high voltages is that first of all, they reduce on the power loss. That means a big voltage will cause, because the power will be lost due to heating. When we have big voltages, it won't affect the end result. At the point where this power is going to be consumed, we'll be having something that can be, we'll be having a voltage that can be used well, instead of when we would have a small voltage being transmitted. We will find that most of it would be lost during the transmission, and at the end of the transmission, where we are using this energy from, we'll find ourselves that we don't have enough energy to be used. So the reason why we have step-up transformers is to step up our small voltage at the power station to a high voltage for transmission. And that high voltage is because we need to have low power losses as we transmit, and to reduce more on the power losses, even the cables that are used in transmission are made thick such that the resistance in them is small. And when the resistance is small, that means even the power lost due to heat will also be small. So you please note that down. Okay, so after that, they have told us that the energy is then now, they have told us that the energy is then now stepped down in phases using the step-down transformers to heavy factories, to industries, to cities, to towns, and then homes. Because the power that is needed, or the energy that is needed to be used in homes, it is not the same power that can be used to run a whole factory or a whole industry. So the phases on which those the energy is stepped down varies from what does that energy do to a specific place. For example, a factory will need a lot of energy than a home because it's going to be running heavy machinery, and for you, you are going to be running your television set, maybe some lights, then cooking some water and so on. Whereas industries will have a lot of things for that. So the phase through which your power is stepped down will not be the same because they don't need the same energy as you. So briefly, that is how transmission takes place. Energy is produced at the power station. It is stepped up by a step-up transformer to high voltages. And we have given the reason why high voltages: to reduce power losses due to heating effect. And to reduce more power losses, we also use thick transmission cables. And then after this power has been transmitted, it is then stepped down so as to be consumed by homes and other people who use electricity power. That is for transmission. But then we have talked about things here that need us to get better knowledge. If someone talks about a step-up transformer, what does it mean? If someone talks about a step-down transformer, what does it mean? Such that when we finish transmission and we have learned the transformers, then we can go now and start looking at how is this power consumed? How is it consumed? So for now, I want us to share about transformers. But before, they have given us some notes here that transmission can either be overhead. That is why someone was telling us electric poles. But some people also make it pass underground according to how safe it can be. And then they have told us that in some countries, they use grid system. Now for us here, if they are to maintain a certain power station, they will have to warn us in advance that on 12th, from this time to this time, they are going to be working on a power station of this area. So these areas, Chanja, those ones, Chisasi, you are going to be affected by that. So the power will be off from this time to this time. Now, why they do that? Because we don't have the grid system. But if it was on the grid system of transmission of power, what they do is they network. The power stations are on a certain network, or they are interconnected, such that in case one fails to work, then the other can supply power. Or in case one is being maintained, then the other can supply power. So for those people or those countries which have grid systems, they don't have such issues where they will take off power to maintain a power station. Power remains there all day long, 24/7, all year running. That is if other factors are constant. For example, if the problem is not at the power station where the power is being generated from, and it is in the transmission, then for them who are on the grid system don't face the load shedding. So someone in the chat is asking us a question that why are there power losses? Power losses are there because as power moves from one place to another, it is moving through materials. For example, copper wires, let me say. So those wires that are used have resistance in them. Remember, resistance is opposition to flow of current through something. So why are there power losses? Some power is lost as we are overcoming the resistance in those materials that are used to transmit the energy. I think my friend in the chat who had that question, your answer is cleared now. Okay. So Andrew, you promised in the chat that you're going to talk about the step-up transformer. We have transformers here. We have one is a step down, the other is a step up. These ones are not on the scale of the ones that are used at the power stations, but they can help us get a picture of what these ones are. So in diagrams, you can see I have two diagrams. The upper one is a step down. The lower one is a step up. What else do you see in the diagrams that we can use in our explanations? Yes. Understand. Seen some hands up. Yes, Linda, your hand is up.
I think we can use the coils to explain a transformer, generally as a step-down transformer.
So can you try to explain to us?
To me, I think a transformer is a step-down transformer is one which is used to reduce alternating current. For example, it converts high voltage from the primary coil into low voltage in the secondary coil. That's what I think.
Come again?
The step-down transformer is the one which is the type of transformer which is used to reduce alternating current. It can convert a high voltage.
From what?
It converts a high voltage from a primary coil into a low voltage in the secondary coil.
Okay. Any other thing? Any other person who can talk about the transformers according to the diagrams that we have? Andrew?
Thank you. Now, the step-up transformer it is like a type of electrical transformer that increases the voltage of any alternating current. Electro signal, it is designed to step up the voltage of the input signal to a higher voltage output, making it suitable for long distance transmission or using high voltage appliances. You get me, master? Now, there is what we call the primary coil. Receives the input signal at a lower voltage. And there is the magnet field of the transformer. That's a voltage in the secondary coil. So that's what I know.
Okay.
Yes.
Thank you, Andrew. Aggie, you have your hand up. Aggie, your hand is up, please. You unmute and talk to us if you are still there. If not, Treasure can talk to us.
Okay. According to what I see, if the number of turns in the secondary coil are more than those in the primary coil, then it's a step-up transformer. Then if it's vice versa, and the number of turns in the secondary coil is less than that in the primary coil, then it's a step-down transformer. And then the step-up transformer increases the value of alternating voltage, while the step-down transformer decreases the value of alternating voltage.
Okay, thank you so much. Okay, so we have two transformers, like we have them in the diagram. One is a step down, then the other is a step up transformer. And according to what we see, you realize that we have a primary coil. We have primary coils in each of them. Sorry. We have primary coils. We have a primary coil in the step down, and we have a primary coil in the step up also. Now, when you look at the primary coils that we have there, you realize that a coil in the step down has more turns than that coil in the secondary. And the coil in the primary coil of the step up has less coils than the secondary coil. But you realize, according to what we have been talking about, voltage in a step down comes when it is too much and then goes out when it is little. Then voltage in a step up comes in when it's of a small value and goes out when it's of a large value. What does it mean? Because the primary coil is our input coil, let me say like that. It's where our voltages are entering from. They are the input coils. So it means that the number of coils, first of all, is directly proportional to the voltage that is there. So if we have few number of coils, that means that even the voltage that is going to be generated from that place is going to be low voltage. And when we have many coils, that means high voltages are at a place where we have many coils. So our electricity or our voltage comes in a step-up transformer when it is small. If you can see there in our diagram, we have an example. They told us that it enters when it is 110 to 120. That is for a small kind of transformer, because this is just getting us a picture of what happens there. So when it enters as 110, according to the number of coils, it goes out as 240. That means it has been increased. That is what a step up does. It will increase your voltage according to how you will use it. Then also, the other thing is that in the step down, the voltage comes in when it is high, and then it goes out when it is low. So these transformers at our level, they can ask us for the transmission, how they help in transmission of energy. So we know how they help. A step up is used to step up during from a small voltage to a high voltage for transmission. Then a step down steps it down from a high voltage to a small voltage for consumption. Then someone can also give you a calculation, tells you voltage entered the primary coil when it is of this value, which voltage was given out, maybe from a step up or a step down transformer. So I want us to also share about the calculation bit of it. How do we get these things working? So like we said that the number of coils, sorry, the number of turns in a primary coil or in any coil is directly proportional to the voltage in that coil. It means, you're going to help, excuse me, and I share a white screen so that we can write there. It means that if I get the ratio of voltage, maybe in the primary coil, and I divide it by the voltage in the secondary coil, this one will give me the same value because they are proportional. It will give me the same value as the number of turns in the primary coil, then divide by the number of turns in the secondary coil. So you can note it down. V is for the voltage. V is for the voltages that we have. And then N is for the number of turns. Number of turns. So that means that if I'm given the number of turns for two of them and one of the voltages, I can really get the other from that expression. So that expression is called the transformer equation. It can help us calculate any of those things that are missing. So someone is asking me, what are the turns? Now, if you look at our transformers in the coils, you have seen that we have a wire coming in, and then that wire is rolled around something like this. So those rolls that are made, those rolls there are what we call turns. Let me show you here. Now, when you look at this coil here, in our diagram of the step up transformer, you realize that you have this one, this. So those ones there are the turns. 1, 2, 3, 4, 5. They are the number of turns in a coil. So when I talk about turns, how many rounds has our wire made on the iron core is one that we call the turns. So someone is asking me what is the name of the formula. The formula is transformer equation. The formula is transformer equation, and it helps in calculation of values that involve transformers, questions that will involve transformers. Voltages. Now the P is for output. The P is for input because the primary coil is the input coil. So this is the input. Then the S, which is the secondary coil, is the output. So energy comes in the primary coil, then it's output in the secondary, and that equation is called the transformer equation. Now we are going to try out some questions here, but before we do the questions, I want us to come up with an expression for how efficient a transformer can be. How efficient a transformer can be. What can be the efficiency of a transformer? How can we calculate efficiency of a transformer? After knowing the efficiency, then we can go on and calculate. Why were we talking about efficiency of a transformer? A transformer cannot give us exactly what we get. The power that we get in cannot be equal to the power that we get out because of some reasons that we can also find. So that means that a transformer can also be efficient like other machines in the work that it does. If it is a step-up transformer, how efficient is it in stepping up the voltage? Or if it's stepped down, how efficient is it in stepping down the voltage? So efficiency, we know that from our machines, we can describe it as work, the ratio of work output over work input expressed as a percentage. But now for a transformer, instead of work, we are going to use power. Power out divide by power in, then times 100%. So times 100%. I hope I don't forget. So power, from our electricity, we know that power is equal to IV. So that means the power out is in the secondary. So we'll have the current in the secondary times the voltage in the secondary, divide by the current in the primary times the voltage in the primary times 100%. So the value that we get is the efficiency of the transformer. Okay, so we are going to do some questions. You are going to excuse me. I put the document which has questions on such that we can calculate through. and we see if we can get the answer. Someone is asking, what does I stand for? I is for current, please. I is for current. Okay, so we have a question. I lost the question. We have a question here. It says that a transformer has 200 tons in the primary coil. Sorry. Yes, a transformer has 200 tons in the primary coil. They're asking us to calculate the number of tons in the secondary coil if 240 volts is stepped up to 415 volts. So that means that we are on a step-up transformer from a small voltage to a big voltage. We have the number of turns in the primary coil. They want the number of turns in the secondary coil. That means we have to use the other equation that we used. So anyone I think we can all try it out and we see which answer we get if it's the same as the one we have here.
Yes, loud. See, you're raising your hand. Talk to us. Love, can you speak to us? Area banks? Can unmute?
The answer is 345.3.83. But I'm asking, are we supposed to put the units there? The answer is 345.83. But I'm asking, are we supposed to put the units there?
For the units, let's wait for the teacher because I even don't know.
Okay.
Maritham, you please share some rights with me so that we can continue. Okay, so which answers do we have? Someone was talking about 300. What? Someone to give us the answer. 300 and, because here I'm seeing 346, but they might have a rounded off, if I'm not mistaken. So which one do we have as the answer? So you please round off to a whole number because we are talking about tons. We can't have a ton which is not full, eh? So when you get 348.88 something, you please write it there. And it's okay if we put tons because we need to know what are we writing there. So those ones who are asking for units, you please put them there. 346 tons. Okay, that is for that question. Pauline, your hand is up. Itham, you please share with me some rights so that I can give people permission for. Yes, Pauline.
I was just telling you the answer.
Oh, okay, thank you. Okay, let us see. Do this other question. There is a question I'm going to type, and we do it together to see which answers we get.
Okay, sir.
Please mute your devices. Let us try that question and see which answer it gives us for the voltage in the secondary coil and then the power output. Okay, I had muted myself so that you can get the answers, but I realized that there is something missing in our second thing where they're asking us for the power output. And I think we are going. There is something that is missing because they have to give us either current such that we can be able to determine the power. But for now, I want us to get at least the voltage in the secondary coil. So we have 60 divided by 200 as the number of coils. And this is equal to VP. VP, we have the voltage in the primary as 240, but we don't have voltage in the secondary. So in the secondary, we have VS. So when we cross multiply, you will find out that we have 240 240 times 200 200. If we divide through by 60, the answer we get will be equal to VS. And that one will give us our voltage in the secondary coil. I hope we all have it. So what is the answer? The answer is about 40. So the answer is 800. Hope we have all got that answer. 800 volts for those ones who have done it. Okay. Now in our group, in our WhatsApp group, I'm going to share more questions when I've written them properly well for you. So you answer those questions. Then in our next lesson, we are going to be talking about how power is consumed or power consumption in our homes. We are going to talk about the wiring. We are going to talk about the color codes in the wires of appliances. We are going to talk about how to count a unit of electricity, the units that we have for your car. How do we calculate them in terms of current, in terms of voltage, in terms of resistance of an appliance? And I think our next lesson, we'll have finished everything to deal with power distribution and consumption. So you allow me today to stop here. I'm really so sorry for the network issues that we had to start late, but I promise that in our next lesson, everything will be so well. So I'm going to request one of you to thank God for us for the lesson, and then we stop from here. Okay, Linda. Linda. Itham, you give Linda rights to unmute so that you can pray for us.
Mighty King of glory, Abba Father, we thank you for this day. We thank you for the gift of a new day. We thank you that we are able to attend this lesson. As we're going to our respective places, as we're going to do other things, I pray that you guide us. Continue to bless us with the knowledge that comes from above. We are sorry for how we have not done according to your will. Bless our teacher and bless everyone. We worship you. There is none like you. In Jesus' name we do pray and believe. Amen.
Amen. Thank you so much, Linda. And thank you all for attending. I'm going to share the things that we have used, the notes and the questions in our WhatsApp groups. so that we can all be able to enjoy the lesson like it was. For those ones who are not in the groups, you talk to those people who gave you the links. They will link you up in the group so that you can receive all the information. Otherwise, you have a very, very nice afternoon and evening. We meet again next week. Bye.
Thanks, teacher.
Bye.
Thanks,
Thank you so much, teacher.
guys, man.
Thank you, teacher.
Somebody's making noise.
Thank
Thank you
you
so much. Have
May
a
God
Join
bless
the
you.
WhatsApp group.
Please join some of us in the WhatsApp
Guys,
group.
how can we join the WhatsApp group?
Hi,
Members,
guys.
thank you for attending the
Bye,
lesson.
teacher.
Hello, guys. How can we join the WhatsApp
Hi,
group?
people.
Guys, we want to enter the WhatsApp group.
Members,
Okay.
also add us in the
Guys,
WhatsApp
tell
group.
Is teacher still
Thank
around?
you.
about the WhatsApp group, guys.
Please join us in the WhatsApp group. So it's just for the name of the group we're going to form.
I don't know. Anyway,
Guys, send the link.
yeah, keep a message. Oh, okay.
Guys, can you please send the link in the chat?
Oh my God. Guys, who is KYF? Anyway, guys, nice time. Thank you so much for joining. But I would love to join the WhatsApp group.
Man,
Teacher, I would
I
like
don't
to
know
join
where
the
the
WhatsApp
WhatsApp group.
group.
Who is it?
Guys, don't leave me out.
Guys, bye.
This is you the
Bye.
link.
Thank you so much, guys. Good night.
That's
Bye, guys.
Yes, just